Section 7.2, Right Triangle Trigonometry. In this section, we're going to introduce the trig functions that we'll be working with through the rest of the semester: sine, cosine, tangent, a few others. And there are a couple different ways that we can think about or define these functions, but the inputs are going to be angles. I kind of alluded to this earlier. So we can use right triangles. So here is an example of a right triangle here. This is one way that we're going to define these functions. We'll define them in terms of the proportions of these three sides. So there's the opposite side, like if we're focusing on this angle theta here, we call this side B the opposite side because it's on the opposite side of the triangle from the angle. The adjacent side, this is the side that is closest to the angle, but not the longest side. The longest side we call the hypotenuse. So C is the hypotenuse. This is always going to be the longest side of the right triangle. It is opposite to the right angle. Okay, so right triangles, that's one sort of pathway towards defining these trig functions. We can also use the unit circle. We're going to talk about this a little bit later. But notice that if we have any given right triangle, we have this associated similar triangle. Remember the section on similar triangles from the beginning of the semester. And if we just look at this small triangle that fits inside of the unit circle, it's going to have a hypotenuse of 1. That's equal to the radius of this unit circle. We're also going to see a way that we can define the sine and cosine functions using the unit circle. Okay. But for now, first we're going to start by just using this like opposite, adjacent, hypotenuse sides of a right triangle to define these trig functions. A couple things to remember before we get into the definition. Remember, we have the Pythagorean theorem that says a squared plus b squared equals c squared. So, a and b are going to be the shorter side lengths, and c is going to be the hypotenuse. So we have that relationship between those three sides of the triangle. And yeah, like we mentioned, a side opposite to the right angle is the hypotenuse, and then we have the adjacent and opposite sides. A couple of important triangles to remember, and we discussed these in the very beginning of the class. We have 45, 45, 90 triangles. And that triangle looks something like this. Oh, let me do a little better job there. Looks kind of like that. And what makes it a 45, 45, 90 is, of course, it has this right angle here. And then these two angles are both 45 degrees. That makes these isosceles triangles, meaning that these two short sides are equal to each other. And remember, we have this relationship, the proportions between these sides. These two sides, the short sides, are equal. So I think the way we sort of talked about this before is like, okay, those two side lengths are x, and the hypotenuse, the length of that, is going to be x times the square root of 2. Okay, and I have a couple of versions of this triangle, or particular 45, 45, 90 triangles memorized. One of them has side lengths 1, so 1, 1, and then the hypotenuse would be then root 2. Or another version of this is going to be a little bit smaller than this one, where the hypotenuse, I set that at 1. And then the two side lengths, again, going with the proportions, like I know that if this is x, we could solve for that because we know that 1 is going to be equal to x times root 2. Right? So then we see that x is equal to 1 over root 2, solving for x. Okay, or if we rationalize that, we end up with root 2 over 2 would be the lengths of the two sides. Okay, so we've discussed this before, but I just wanted to remind you. The particular triangle 45, 45, 90 that's nice to work with in this section is this one. I like this one where we have the two side lengths are 1 and the hypotenuse is root 2. We'll see why in a little while. The other one is the 30, 60, 90 triangle. And this triangle looks a little more like this, where of course we have the right angle, and then we have a 30-degree angle over here, and then we have a 60-degree angle over here. And the proportions between these side lengths, we call the short side x, the hypotenuse is 2x, and this side over here is x times square root of 3. All right, so some particular 30, 60, 90 triangles that I sort of just have memorized. There's one where I let the short side be 1, and then the hypotenuse is 2, and the other side is square root of 3. That one's really nice and easy to remember and easy to work with. Just don't confuse it. Sometimes I see people accidentally putting the other side length as 2 and the hypotenuse is root 3. Be careful not to make that mistake. I always just remember that the hypotenuse is twice as long as the short side. So that's one of them. And another one that we'll see, and this is the one that will pop up inside of the unit circle when we start talking about the unit circle, is where we set the hypotenuse to be of length 1. So then the short side will be just half of 1, which is 1/2. And the longer side will be root 3 over 2. Okay. And the triangle that's easiest to work with, that's helpful in generating the outputs of our trig functions that we're going to define in just a moment, I prefer this one for this section. Okay, so the first part of this and us sort of being effective at working with these trig functions is having these triangles memorized. It's going to make a lot of the work go a lot quicker going forward. Okay, let's define these trig functions. So trig functions in the right triangle, this sine function, sine of theta. So first of all, before I discuss how we get the outputs, note that the inputs are angles. So I'm using theta as the variable to represent the input. So the domain of these trig functions are going to be like we're pulling them from, either from the unit circle or from triangles, the interior angles of triangles. All right, and here's how we define these. We're going to use a right triangle. So I'm just going to draw sort of a generic, non-specific right triangle. This isn't necessarily going to be a 45, 45, 90 or something like that. And we'll call this interior angle here theta. All right, and remember the way that we define these sides, or the names we give these sides. The side on the opposite over here, opposite from theta, is the opposite side. And then we have the adjacent side. And we have the hypotenuse, which is the longest side opposite to the right angle. Okay, so to find sine of some given angle, we're going to think about the associated right triangle with that angle, and the output of the function is going to be the ratio of the opposite side, whatever this side length is, divided by the hypotenuse, whatever that length is. Cosine, our second trig function, is going to be adjacent over hypotenuse. So using the same triangle, using the same angle, we're just going to then take the quotient adjacent divided by hypotenuse. Whatever that number is will be the output of cosine. And tangent is going to be opposite over adjacent. All right, so to abbreviate this, I might write this as O over H, A over H, or O over A for tangent. Again, another thing that we're going to have to memorize, but I have some little mnemonics that are helpful for remembering this. So the order of these trig functions, generally we think sine, cosine, tangent. Whoops, tangent being number 3. And the mnemonic that I use is, so we have O, H, A, H, O, A. And the one that I learned back in whenever, high school, Oscar has a heap of apples. Oscar has a heap of apples. That's what I use to remember the order of these numerators and denominators to define these trig functions. Another one that I've heard, old hippies all high on acid. That's another one you can use. Don't quote me on that one. Another common one that maybe you've seen before is SOHCAHTOA. Okay, so sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Okay, so whatever works for you, Oscar has a heap of apples, SOHCAHTOA, it's up to you. This all might seem kind of abstract right now. Let's see an example and see how we actually use right triangles to find outputs or values of trig functions. Example 1, we're given this triangle. We're given an angle. This is a 3, 4, 5 triangle. These are really pleasant little right triangles. The proportions work out so that we have these nice consecutive whole numbers as the side lengths. So here's our angle theta. We want to evaluate sine of theta, cosine of theta, and tangent of theta. Now, the nice thing is to find sine of theta, normally if we're going to evaluate a function at some number, it's like we want to know what is theta, like how many degrees or how many radians is that angle. If we're using right triangles, kind of the nice thing about right triangles is we actually don't need to know what the angle is to evaluate the trig function at that value, as long as we have all 3 sides of the triangle. So for sine of theta, I'm going to highlight theta so that we're clear on which angle we're sort of referencing off of. There is the angle theta. Sine of theta is O over H, so opposite over hypotenuse, or Oscar has. So for this triangle, we just have to figure out, okay, what is the opposite side relative to theta? What is the hypotenuse? So the hypotenuse is easy. It's always going to be the longest side, the one that's opposite to the right angle. So I know that the hypotenuse is going to be 5. I can write that in. Now, how about the opposite side? Opposite is going to be over here, right? This is opposite. This is adjacent. Adjacent means it's next to the angle. So we want the opposite. 4/5. That is going to be sine of theta. Okay, so it just outputs that ratio there. How about cosine of theta? Okay, Oscar has a heap. So adjacent over hypotenuse, what is that going to be relative to that angle theta? Well, the adjacent is 3. The hypotenuse is 5. So there we go, 3/5. That's going to be cosine of theta. Now how about tangent? Tangent of theta is of apples, or TOA, opposite over adjacent, so that will be 4 over 3. All right, so that's how we would use a right triangle to find the values associated with sine, cosine, and tangent. Let's keep going. We have just a few more trig functions to define here. Now we have cosecant, secant, and cotangent. Maybe I'll write out these names so that we can see how they're spelled. Cosecant secant and cotangent. We call these the reciprocal trig functions because they're obtained by just taking the reciprocal of sine, cosine, and tangent. So cosecant, denoted C as c of theta, is just 1 over sine of theta. So the reciprocal, just flipping the fraction. That's why the output of this can be found by looking at the hypotenuse over the opposite side. Okay, so rather than opposite over hypotenuse, Oscar has, we have hypotenuse over opposite for cosecant. Secant is the reciprocal of cosine, so hypotenuse over adjacent, and cotangent, reciprocal of tangent, is adjacent over hypotenuse. Okay, so I don't have another mnemonic for H, O, H, A, all that. I don't think it's really necessary. Just remember that cosecant is the reciprocal of sine, secant is reciprocal of cosine, and so on, and we just flip the fractions. Okay, example 2, we want to find the exact values of all 6 trig functions. That's sine, cosine, tangent, cosecant, secant, and cotangent for this given angle theta in this triangle. Okay, so I might start by writing out, I want sine of theta, cosine of theta, tangent theta, cosecant theta, secant theta, and cotangent theta. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Cosecant will be the reciprocal of sine. So hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. So just checking, Oscar has a heap of apples. Okay, that's all good. And then just getting the reciprocals for each of these, that all looks good to me. Okay, so I'm kind of oriented now. Now let's look at this triangle. So if I want to find sine of theta, I'll just use opposite over hypotenuse. So that will be 2 over 5 in this case. And again, since we have these side lengths, we don't need to worry about the exact actual measurement of theta. We can just output 2 over 5. So that's good. Now for cosine, we'll do adjacent over hypotenuse. Okay, and I know this is the hypotenuse, that's the long side, opposite to the right angle. Adjacent is going to be this one that's right next to our angle theta. We are not given that value. So what is A? We're going to have to find it. How can we find this missing side length given that this is a right triangle? So that's what we're going to do, a little aside here. Let's find A. Now remember, right triangles have this great property, this theorem, the Pythagorean theorem, tells us that A squared plus B squared equals C squared. Okay, and we're looking for A. We happen to know the other side length is 2, the hypotenuse is 5. So we're going to solve for A in the Pythagorean theorem. So A squared plus 2 squared is equal to 5 squared. So I want to solve for A. I'll start by just simplifying. I can multiply this out. This is 4, this is 25. So A squared will be equal to 25 minus 4, just subtracting 4 from both sides, trying to isolate A. So A squared is equal to 21. Now, the last thing that I have to do to get A by itself is I'll have to solve by taking square roots. I'll take the square root of both sides. And remember, when we have a square root of something squared, like this, it does introduce a plus or minus. Okay. Oops, sorry, there should be a square root there. Okay, but since we're talking about the length of a triangle side, it doesn't make sense to have a negative value. We're just going to take the positive one. So we get a is equal to the square root of 21. Does this simplify at all? Square root of 21? Well, you know, I could search for perfect squares inside of 21, but the prime factorization of 21 is just 3 times 7, like that. So see how there's no perfect squares in there. So root 21, that's just what we're left with here. Okay, so now we know the adjacent side is the square root of 21. All right, so a little side quest there. But now that we have that adjacent side, we could kind of blast through the rest of these. Cosine of theta will be root 21 over 5. And now tangent will be opposite over adjacent, so 2 over root 21. But I might rationalize that denominator. Remember, we don't like to have radicals in the denominator, so I'll multiply by root 21 over root 21. And I get 2 root 21 over 21, right? Because root 21 times root 21 is just going to give us root 21 squared. Cancels out, leaves us with 21. Okay, cosecant, this is going to be hypotenuse over opposite, or just the reciprocal of sine, so 5 over 2. Secant is going to be adjacent over hypotenuse, which will be, hypotenuse over adjacent, so 5 over root 21, or if I rationalize it, that would be 5 root 21 over 21. And cotangent will be adjacent over opposite, root 21 over 2. So I'll box these up. These are my 6 answers for the outputs of our 6 trigonometric functions. And you know, you can sort of check also, like, just ensuring that these are, you know, sine and cosecant are reciprocals of each other. Like I always like to look things over a couple times to make sure everything looks right before I move on. But I think we are good on this one. Moving on to page 6, example 3. Now we want to evaluate these trig functions at some particular angles. So notice here we aren't given a picture of a triangle. We're just given the input. Like here we want to evaluate sine at 30 degrees. So far we only have defined these trig functions in terms of the sides, or the, you know, the relationships, the proportions between the sides of a triangle. So if I'm looking for sine of 30 degrees, I need to come up with a triangle with a 30-degree angle, a right triangle. So the first step for any of these, part A through D, is we want to come up with the associated right triangle with the angle. So sine of 30 degrees, what does an angle or a triangle with a 30-degree angle look like? It's going to look like this, and this angle, I'll have that be my 30-degree angle. Okay, so if that's 30 and this is a 90-degree angle, we know that this remaining angle must be 60. This is a 30, 60, 90 triangle. Now this is where it really comes in handy to have the side lengths memorized. So it doesn't matter which 30, 60, 90 triangle we use, because it turns out that, all of the different 30, 60, 90 triangles are similar to one another, meaning that the side lengths are going to be proportional. So since sine is defined as a proportion of, the opposite side over the hypotenuse, it's not going to matter which 30, 60, 90 triangle we use, just pick one. My favorite one is the one with the side lengths 1, 2, and root 3. Okay, remember where the hypotenuse is twice as long as that short leg. Now that I have this, remember this is my angle theta, which is 30 degrees in this case. Hypotenuse is going to be 2, that opposite side is going to be 1, so sine of 30 is going to be 1 over 2. All right, so kind of interesting, like the way I introduced these functions, as I said, they're these kind of trippy functions. They have relationships to right triangles, but the inputs are angles. So we're evaluating this sine function at the angle 30 degrees. We get an output of 1/2. Let's look at cosine of 45 degrees. So again, we only really understand these currently in terms of right triangles. So let's draw a right triangle that has a 45 degree angle in it. Let's call this theta. This will be our 45 degree angle. And what must this other angle be if this is 45 and this is 90? Well, it must be 45. Just a reminder of why that is. Remember, the sum of these three angles, like if this is the triangle A, A, B, C. Remember, angle A plus angle B plus angle C is equal to 180 degrees, right? That's true for any triangle. So if angle A is 45 and angle B is, unknown, and angle C is 90, see how we could just solve? We could solve for angle B. Ends up being 45 degrees. Okay, so let's figure out what the side lengths are. Again, I get to pick which specific 45, 45, 90 triangle I want to work with here. And I said a couple pages ago, I like this one. 1, 1, root 2. Okay, cosine of this angle, 45 degrees, is going to be adjacent over hypotenuse. So here's the adjacent side. Here's the hypotenuse. So this is going to be equal to 1 over root 2. Or, rationalize the denominator, multiply top and bottom by root 2. And I get root 2 over 2. Okay, so see how we're just generating these triangles and coming up with the outputs of the trig functions. Now sine of 45 degrees for part C, I don't even need to draw another triangle. I'm just going to use the same triangle that I drew right here. Because it's the same angle, I just want to know the sine. So rather than adjacent over hypotenuse, I want to know opposite over hypotenuse, which actually ends up being 1 over root 2. Same as cosine. So root 2 over 2 is also going to be the output for sine. They have the same output given an input of 45 degrees. Okay, how about this one? Cotangent of 60 degrees. So 60 degrees, let's draw a triangle. Let me be careful here. For this, I'm going to draw this triangle. This right here is my 60 degree angle, right? So then that other angle must be 30. This is a 30, 60, 90 triangle. So I'm going to label the sides 1, 2, and root 3. Again, just those proportions that I have memorized. I want cotangent of this angle 60 degrees. So cotangent So remember, cotangent is the reciprocal of tangent. So this is the same as 1 over tangent of 60. So tangent of 60, remember it's going to be, Oscar has a heap of apples, so of apples. So cotangent is just going to be the reciprocal of that, A over O. So adjacent side over the opposite side. So let's find those sides in the triangle. Adjacent side is 1, opposite side is root 3. So then cotangent of 60 degrees will be 1 over root 3, or rationalizing the denominator, we'll get root 3 over 3. Something to point out for part D. I drew this triangle here, which is a 30, 60, 90 triangle. It's actually the same triangle as this one over here that we used for part A. So I actually could have just looked at this triangle and thought, okay, you know, that angle right there is the 30 degree angle, so this must be the 60 degree angle. I could have just looked over here rather than drawing it again and thought, okay, what is adjacent over opposite? That would be 1 over root 3. Okay. I drew it again over here. I sort of have the habit of drawing the triangle each time. I also kind of like drawing it in that sort of standard position where, you know, the initial side is like if we drew the XY coordinate system here, it's like the initial side is on the positive x-axis, and then, you know, terminal side is wherever it ends up, 60 degrees north of there. I'm in the habit of drawing out the triangles like these, but just so you know, if you have a problem like this, you could totally recycle this picture and use it to find the cotangent of 60. Okay, how about example 4? We want to find the unknown values in this triangle. So this is a triangle ABC. We see a right angle here at angle C. The opposite side is 4 root 3. We're given that this angle alpha, which we could also call angle A, or, you know, using the angle notation, angle BAC. That's another way that we could express that. That's 60 degrees. I'm pretty happy to see a 60 degree angle, because then I know that this is a 30 degree angle. And I know some stuff about 30, 60, 90 triangles. Okay. But we want to find all the unknown values. So I actually already found one of them, because, you know, we want to find what is this angle, and we want to know what are the lengths of these two legs of the right triangle. Okay. So we could start by doing what I did very quickly without even really meaning to. If we want to find this angle beta, let's start there. Let's find the angle beta. Okay, and that's just from the Greek alphabet. We know that alpha plus beta plus that right angle, which is, you know, 90 degrees. Maybe I'll just call it 90 degrees. Should be equal to 180 degrees, because this is true for any triangle. Add up all the angles, you get 180. So I know that alpha is 60 degrees. Beta is still unknown. Plus 90 degrees should be 180. So I will just solve for beta, subtract 60 from both sides, subtract 90 from both sides. and I'll get that beta is equal to 180 minus 60 minus 90. That's the same as 180 minus 150. I get 30 degrees. Okay, so just showing where the math comes from. I'll put a box around that. That's one of my unknown values. Okay, so now let's turn our attention toward these side lengths. Now to find B and A, this is a 30, 60, 90 triangle. I could totally use the proportions to sort of figure this out. How might I use trig functions to do this instead though? Let's, how about start with A? So let's find A. And I want to show you how I would use a trig function to do this. So what is a trig function that would relate some of our known values, so maybe like this 60 degrees and maybe this 4 root 3 and this side length A? What is a trig function that will tie together those three values? Because what I see is like, okay, two values that I know, one value that I want to know. If I can set up an equation using a trig function, I might be able to solve for A. So, okay, relative to this angle 60 degrees, this is the opposite side, right? A is the opposite side. And 4 root 3 is the hypotenuse. So which trig function utilizes or involves the ratio of opposite and hypotenuse? Well, sine does. So sine of 60 degrees is going to be equal to opposite over hypotenuse, opposite being A, hypotenuse being 4 root 3. All right, so I now have this equation with one unknown value, which is A. So let me solve for A real quick just by multiplying both sides by 4 root 3. So 4 root 3 times sine of 60 degrees is equal to A. So this is just some number, but I'll have to evaluate this to figure out what that is. What is sine of 60? Sine of 60, I can figure this out using one of my sort of generic right triangles. So, you know, I drew it up there. I'll just draw it again right here. So 60-degree angle, if I draw the triangle associated with that, here's our 60-degree angle right here. 1, 2, root 3, just using that generic 30, 60, 90 triangle I like to work with. If I want sine of this angle, it's going to be opposite over hypotenuse, so root 3 over 2. So this is 4 root 3 times, and then I find that this is equal to root 3 over 2. And that's equal to A. Okay, so I know that I'm working with this triangle over here, but in solving this equation to find this value A, I use this 30-60, this generic 30-60-90 triangle over here. Okay, now I just simplify root 3 times root 3, so I could write this as, 4 times root 3 squared over 2 is equal to A. Root 3 squared is just 3. So we'll have 12 over 2. It looks like A is equal to 6. Very nice. Okay, so we used sine of 60 to solve for A. I think the last thing we need now is just B. So last thing we want is B. What is that side length B? I could do something similar to what I just did here. I could use sine of 30 degrees, or I could use cosine of 60, right? Because if I look at cosine of 60, that will be adjacent over hypotenuse. Again, I would be setting up an equation with B being that only unknown value. But just to keep things interesting and to remind ourselves of how to use another formula, now that I have two side lengths, I could just use the Pythagorean theorem to find B. So down here, let's find b. Okay, I know that a squared plus b squared is equal to c squared. I know that a is equal to 6. B is unknown. C is 4 root 3, so we'll square that. 6 squared is 36. 4 root 3, that's going to be 4 squared, which is 16 times root 3 squared, which is 3. Okay, keep working over here. I'm going to get that b squared is equal to, okay, 16 times 3 is 48, and then I'll subtract 36 from both sides. B squared is equal to, I'm getting 12. So B equals, I'm going to take the positive square root of 12. Don't need the negative, because remember, this is side length of a triangle. It must be positive. This I can simplify. Root 12, I could write this as 2 times 2 times 3, right? So these 2 copies of 2, that's a 4. What's the square root of 4? Just 2. So this is 2 root 3. So there it is. We have that b is equal to root 3. Excuse me, 2 root 3. Okay, so I'll write these in. 2 root 3 was that side. A was equal to 6, and beta is equal to 30 degrees. All right, so that's how we could use trig functions to solve right triangles. Now, looking at example 5, we've got another triangle we want to solve for a couple sides here. We want to find side length B and C if A is equal to 4. So A down here, this is 4. And the angle beta is 27 degrees. So that is this angle down here. Okay, so 27 degrees is not a super friendly angle. You know, it's not going to give us a 30, 60, 90 triangle or 45, 45, 90. So that's something we're going to have to watch out for here. But let's start by just trying to find a trig function that relates, you know, some known values with some unknown values. So I have beta and I have A. So let's just pick a side and see if we can set up a trig equation. How about B? Let's say we wanted to find B. So I know this angle, I know this side, and I want this side here. So what is a trig function that relates the adjacent side, right? Since beta is our angle that's in focus here, the adjacent side, and also this would be the opposite side. So, you know, we can look back to our trig functions to remind ourselves. Opposite and adjacent. It looks like tangent is going to be the one to use there, because tangent of theta, or in this case tangent of beta, is going to be opposite over adjacent. So let's try and set up an equation there. So the first thing we're doing is we want to find B. And what we can use to find B is we know that tangent of beta will be opposite over adjacent, so that'll be B over A. And then plugging in the values that we have, tangent of 27 degrees, that's beta, is equal to B over A, which we know is 4. And this is looking good. We have just one unknown value, so I should be able to solve for B. I can do that by multiplying both sides of the equation by 4. I get that 4 tangent of 27 degrees is equal to B. Now here's the tricky part, or the part that kind of differs from that last example. Tangent of 27 degrees. 27 degrees is not a friendly angle. I don't know what the tangent of this is. This is where I might actually use my calculator to just, get a decimal approximation maybe for what tangent of 27 is. So let's go over to our calculator for a second and I'll show you how we'll do that. Okay, here is our virtual TI-84 calculator. Most of the Texas Instruments calculators will look pretty similar to this one. I use the TI-83, the kind of old-fashioned one. But okay, let's see how we evaluate this trig function using our calculator. So the first thing that we're going to do is I'm going to click on Mode, and it'll bring up this menu here. And what I'm doing is I want to make sure that I put this into degrees rather than radians. So you'll see down here, a few levels down, and I could use the directional buttons. I'll go down and I'm going to go over to degree and hit enter. And what this tells my calculator is that whatever value I'm plugging in as an input for my trig function, in this case my tangent function, this is going to be entered in terms of degrees. If you forget to do this, you're going to have issues. Okay, so that's done. I'll hit second and then quit, and that'll bring me back to this main menu here. So now I'm going to hit the tangent button, and I'll plug in tangent of 27. And I can hit enter, and okay, so around 0.509, I'll round eventually. But before I round, I want to multiply this by 4, right? Because that's in the equation that I'm solving. I actually want 4 times this number. So I can do 4 times, and then if I hit second answer, okay, so down here at the bottom, right next to the enter button, answer, that's just going to substitute in whatever the last value that was returned by the calculator was. Okay, so then I'll do 4 times answer and hit enter, and there we have it. That is 4 times tangent of 27 degrees. And this is going to be my B value. I might round this to maybe just a couple decimal places. So how about let's round this to 2.04. Okay, we'll go back to the notes and fill that in. Alrighty, so now we'll say B is approximately equal to 2.04. Okay, and I'll put a little box around that because that was one of the things that we were asked to find. And the only other value we want is C. So now we're going to turn our attention to this one. And we have multiple options here. We could do the Pythagorean theorem and solve for C that way. We could also use another trig function. So maybe just to get practice with trig functions, let's use that method. Next, we're going to find C. So, okay, again, we know what beta is. We know what what A is. We also know what B is. Okay, so we have a lot of options, but maybe just using beta and A again. Which trig function can I use to set up an equation involving beta, A, and now C? Well, this is the adjacent side. This is the hypotenuse. So which trig function involves adjacent and hypotenuse? I think cosine is going to do it. Cosine of beta is equal to adjacent over hypotenuse. Oscar has A heap. So A over C in this case. Okay, and now kind of the same way we did the last part, we'll do plug in the values. Cosine of 27 degrees is equal to 4 over C. That's the unknown. And now we want to solve for the unknown C. So what I might do is multiply both sides by c. That'll get it out of the denominator and to the other side of the equation. So then I'll have c cosine 27 degrees is equal to 4. And now just divide both sides by cosine of 27. So then I get c is equal to 4 divided by cosine of 27 degrees. And I used my calculator for this, and I got a decimal approximation. And this time I just typed it all in one go. You know, I didn't do it in two separate steps like I did finding b up here. I just plugged it in, was careful about, you know, parentheses and all that stuff. And I got this, about 4.49. So that is C. And I'll box that up. Okay, and you know, I'll do a little bit of a sanity check sometimes, you know, like fill in some of the values and make sure everything makes sense, you know. C, that's the hypotenuse. It should be the longest side, and that is the case, 4.49 units. Okay, and then B was about 2.04. Okay, and you know, I could solve for alpha as well. When, you know, I take the difference of 180 minus 27 minus 90, I get that this is actually 63 degrees. Okay, so notice that this triangle is definitely not drawn to scale. And you'll see that this is common in homework problems and, you know, stuff that pops up on My Open Math. It's not drawn to scale. In this picture, it looks like this is the larger angle and this is the smaller angle, okay? But that actually isn't the case. If I could, you know, even redraw this picture to be a little more accurate, because 27 degrees looks more like that. Okay, so then this is 4, this is 4.49, this is 2.04. All right, so this one is drawn to scale. Okay, and oftentimes in problems in textbooks or, you know, on the homeworks, it'll say something like triangle is not drawn to scale, just to get ahead of this. Okay, so if you ever see this, don't rely on what the triangle actually looks like. Don't rely so much on the picture as far as what the proportions should be. You're really relying more on the picture for the orientation. Okay, so just a little warning there. Okay, moving on to example 6. This one has a little more going on. I am seeing multiple triangles, multiple right triangles, and I'm being asked to solve for x, which is this distance right here. All right, so I think this one's going to be a little more involved than the previous two examples, but let's try and piece this one together. So I'm noticing that this value x that I'm trying to solve for, this is a side length of, you know, I guess this triangle right here. But the big problem with that triangle is that it is not a right triangle. And the trig equations, the trig functions only apply to right triangles. So it isn't like we're going to be able to just work with this, you know, little sliver over here and solve for x. We're going to have to get two right triangles that I see in this picture. We're going to have to get them both engaged. So I see this triangle. Okay, so there's a right triangle. I have some options to work with that one. And then I have this larger right triangle. Okay, so I'm going to have to strategize and see how can I find this value x using those two triangles. And, I'm probably going to use some trig equations, some trig functions to try and solve for unknown sides and see if I can kind of reason my way towards that value x. Okay, what I am thinking here is if I can find this side length over here, okay, and maybe I'll call that A. And if I can find this large side length, right? So I'm really just thinking in terms of those two right triangles that I have there. Maybe I'll call this one B. I might be able to, take a difference, right? Because if I take this value B and subtract A from it, I should just be left with X. Okay, so again, I know how to work with right triangles better than, scalene triangles. So I'm thinking, how can I use those two right triangles, find some values, and come up with X? So I think this is going to be my strategy here. Now, I guess starting with A, I want to start by trying to find A because this side, or this angle, rather, is given to me at 20 degrees. Notice that this is not the entire angle for the big triangle, it's just for the small triangle. Okay, so I'm seeing that A is a little bit more accessible at this point, so I might start there. So let's find A. All right, and just like in the previous two examples, I am wanting to find a trig function that will relate, an angle, a side that I know, and the side that I don't know that I'm looking for. So relative to this angle, I have 140 as this side length, and this is the adjacent side. And A is the opposite side. So I want some trig function that relates adjacent and opposite. I think the one that I want is tangent. So remember, tangent of theta is equal to opposite over adjacent, right? Oscar has a heap of apples, or TOA, if you're a SOHCAHTOA person. All right, and I'll plug in my values. Tangent of 20 degrees is equal to opposite is what I don't know. So sorry, this is a little confusing, but that's actually going to be A. Adjacent A is 140. Okay, and then A is my unknown. All right, I'll multiply both sides by 140. So 140 times tangent of 20 degrees is equal to A. And I'll use my calculator again, just like I did last time. And I rounded to 2 decimal places because I got a number that wasn't super friendly. I got approximately 50.96 units. Okay, so we're off to a pretty strong start here. Maybe I'll put a little box around this and I can fill it in on my picture. So that is about 50.96. Okay, good. Now, remember my strategy is to find that side length, and now I want to find B, and then I'm hoping that I could just take a difference to solve for X. So now how am I going to find B? First of all, now we're talking about this big triangle. So let me just outline it so that we know which one we're talking about. And we have that this angle right here is 58 degrees. And I know that this side length is 140. I don't know the hypotenuse, so I don't think that the trig function that I want to use here is going to involve the hypotenuse at all. Since I know that that 58 degree angle is there and the opposite side is 140 and the adjacent side is B, right? Talking about this large triangle. I think this is going to be another tangent. So let's do this. Let's find B. And I want to use tangent. The angle I'm plugging in is 58. And this is going to be equal to opposite over adjacent. So I'll do 140 over B. Okay, and then I want to solve for B. I'll multiply both sides by B, and I'll also divide both sides by tangent of 58. So I will get 140 divided by tangent of 58. Okay, so one more time, what I did there is I multiplied both sides by B, and I also divided both sides by tangent of 58. All right, and I put this into my calculator. And I'm still in degree mode on my calculator. Let's see, I probably should put these little degree markers. If you ever get something from your calculator that makes no sense whatsoever, make sure you're in the correct mode. If you're dealing with degrees, be in degrees. If you're inserting radians, be in radian mode. Okay, and I got from this 87.48. Again, rounding to the nearest hundredth. All right, good. So now that I have this, I'm just going to use sort of a basic geometric principle here. So finally, this is kind of the last step. So I'll say now, I know that B is equal to X plus A. And this just comes from the basic principle that the whole is the sum of the parts. And I know what B is, I know what A is. So B is 87.48. I don't know X. A is 50.96. So I can just subtract 50.96 from both sides. And I get that X is approximately, and I really should have put an approximation symbol up here because I did round to get those two numbers, the 87 and the 50. I took that difference and I got approximately 36.52. And that's what I was asked for in this problem. So I'll box it up and we're all done. Okay, so a few different stages to this. Just remember trig functions, sine, cosine, tangent, the other three, we can only use them in relation to right triangles. So if you ever see a problem like this, try to identify where the right triangles are, see what values, what side lengths, what angles you can find using right triangle trigonometry. And you might have to do some spatial reasoning, apply some other little basic geometric principles to try and find the value or the side length or the angle that you're actually looking for. So this is a great problem to study from. You'll probably see stuff similar to this in the homework. All right, and then page 8, we've just got a couple more examples to finish up the section, a couple applications. So trigonometry has infinite application to the real world, to the sciences, to physics and engineering especially. So let's look at a couple basic examples, see how we might apply trig functions to solve some real world problems. Example 7, we have a 50-foot tower that's located on the edge of a river. I am definitely going to be drawing a picture for this one. The angle of elevation between the opposite bank and the top of this tower is 37 degrees. And the question is, how wide is the river. Okay, let's start with a picture. So a 50-foot tall tower. Okay, I'll start with this. I don't know what kind of tower this is. Maybe it's one of those 5G towers or something like that. Okay, there's my tower. And this is on the edge of a river. So there's a river right next to it. So how about the river is, and also I'm kind of paying attention to this angle of elevation from the opposite bank. The river is going to be on this side, how about? And it'll just be kind of flowing by like that. Okay, there's my river. Don't hate on my artistic ability. Okay, so there we go. And then here's the opposite bank over here. So this point is going to be relevant because we're told that we have an angle of elevation between this opposite bank and the top of the tower, and that is 37 degrees. So I can see a right triangle kind of coming to fruition here. So I might draw it in. I'll draw it in another color. This triangle, and you know what, here maybe I'll be careful to make sure that this looks like a right triangle. It's going to look something like this. Okay, because this tower, you know, the way that we build structures is we want them to be orthogonal or at a right angle to the ground, right? We want it to be all level and plumb. So we'll have a right angle there, and then this angle, the angle of elevation, is said to be 37 degrees. So I'm going to mark this right here, 37 degrees. Okay, another value I have, I know that this tower is 50 feet tall, so I'll mark this at 50 feet. And what I'm asked to find is how wide the river is. So I'll label this with a variable. Maybe I'll just call this x. Okay, so, you know, at the beginning of this problem, I didn't really know what to expect. I didn't know how I was going to apply trig to find this unknown value. But now having the picture and having the triangle, just finding the right triangle, just like we did in this previous example, right triangles are what we can work with well using these trig functions. So where's the right triangle at? Now I can see it. I know what my unknown is, and I think I know which trig function I want to use to try and solve for that unknown. Because I know this angle right here, I know the opposite side, and I'm trying to find the adjacent side. So opposite and adjacent, this is going to be another tangent problem. Okay, so we want to find x. And I know that tangent of that 37 degree angle of elevation is going to be equal to opposite over adjacent, so it'll be 50 feet over x. Okay, I'll multiply both sides by x, divide both sides by tangent. You'll get used to doing that little operation. Sometimes I see people who like to do this, where they do the butterfly method, multiply those two and multiply those two. Whatever you do to solve for a variable that's in a denominator, I'm fine with it. So I'm going to get that x is equal to 50 divided by tangent of 37. Okay, and turning to my calculator, again, you can type this all in one go if you like. Just make sure that you are in degree mode, since we're dealing with degrees in this case. So 50 divided by tangent of 37 degrees, I am getting approximately 66.35. And I have to think, what are my units here, right? This is an application problem. I have to be careful, make sure I include the correct units. This is the measure of a side length. The height of the tower was given in terms of feet. That means that this other side length is also going to be in terms of feet. So the width of the river is 66.35 feet. Okay, so once you draw the picture and decide which trig function you're going to use, it's a pretty straightforward problem. You just kind of have to have the courage to dive in and seek out that right triangle and set up the equation and solve. Okay, we've got one more. Example 8, let's have a look. From a room on the top floor of a nearby hotel, the angle of elevation to the top of the Eiffel Tower is 17.5 degrees. So that's this angle right here in the picture. From the street level in front of the hotel, the angle of elevation to the top is 21.4 degrees. We want to find the distance from the hotel to the midpoint of the base of the tower. And we also want to approximate how high the top floor of the building of the hotel is from the ground. Okay, so kind of a lot going on here. The picture is helpful, right? It just sort of demonstrates like that angle of elevation from the top floor, this angle of elevation from the ground. There's this thing like, okay, but we're talking about a midpoint all of a sudden. Like, what's this about? What is the distance from the hotel to the midpoint of the base of the tower? Here is the midpoint. Really, that is just making the problem easier for us. It's making it clear and not ambiguous, like what the actual bottom point is, right? This isn't just a like telephone pole coming out of the ground where it's clear where the base of the pole is, right? So the midpoint, don't let this throw you off. This is just sort of clarifying what distance we're actually trying to find. And this is really helpful because, remember, we like right triangles. We like when right angles pop up. And if we're talking about, the top of the tower being this point right here, if we just draw a straight line down to the midpoint, that's going to give us the right angle that we're after. Okay. So, and then one other number that isn't written out in the problem, but the height of the Eiffel Tower is 1,063 feet. Okay, so now that I have that right angle, I'm going to draw this triangle here. Okay, that's helpful. I'm definitely going to work with this. Now, the angle of elevation from this top floor in the hotel. What an angle of elevation is it's just the angle from the flat horizontal. Okay, so this right here is just going to be a flat horizontal line. It's going to be parallel with the ground. Okay, so I might even put in these little parallel markers here. Okay, and that's very important because that gives us another right angle right here. Okay, so I'm always more at ease with these application problems once I've drawn the picture and found some right angles. Okay, I know I can work with right angles. All right, so what are we going to do next? What are we looking for? I think that's a good place to start. The first question is, what is the distance from the hotel to the midpoint of the tower? Okay, so that is this distance here. And yeah, maybe I'll just label that with an X for now. Okay, so I am pretty confident that we could find this. I think it's going to be another tangent function, right? Because we have that angle 21.4, we have the opposite side, we have the adjacent side. Tangent function comes in handy a lot. I think we're seeing that in this section. So let's start by finding X. Okay, so I'll say, let's find X, which is what, we just defined it as that distance between the hotel and the midpoint there. Tangent of 21.4 degrees is going to be equal to opposite over adjacent, so that'll be 1063 over x. Solving for x, it'll be 1063 divided by tangent of 21.4 degrees. All right, that looks good. I'll use my calculator. 1063 divided by tangent of 21.4. And I know I'm in degree mode. And I'm getting that x is approximately equal to 2,701 and 12. Sorry, 2,712 point. Maybe I'll just round to the nearest tenth of a foot. 0.5 feet. Okay, so there it is, and maybe I'll just write it out to make it clear. The distance from street level of hotel to the tower is 2,712.5 feet. Good. So we got that part done. What else do we want to know? We want to know approximately how high is the top floor of the building. Okay, so we want to know what this height is right here, and I'll mark it on the picture. We want to know what that distance is right there. Okay, so maybe I'll label that with a Y. Okay, so that line that I just drew in purple isn't even a part of any of these triangles that I drew. So that's a little bit of an issue for me. What I hope I can do here is maybe find an equivalent, like a congruent side somewhere that might be a little more advantageously placed in this diagram so that I might be able to solve for it. So I have a lot of right angles close to y, right? That's going to be a right angle. This is going to be a right angle because we're assuming that this tower or this hotel building is plumb. Okay, and that gives me a rectangle down here. So this down here is a rectangle. And the advantage of that is I know that this opposite side over here is also going to be that same length of y. So over here, maybe I'll write it in green so that you can see it. That purple side length is going to be congruent to this green side length over here. Okay, I prefer the position of that because now I think I'm going to be able to use a similar type of reasoning that I did on the previous page, right? Because if this entire side length of this big triangle here is known, and it's 1,063, and I think that I could use this other triangle to solve for this side length over here. Let's see, I need another color. How about, I don't know, yellow. This side length right here. I should be able to solve for that. Okay, so I'm hoping that I can use some kind of, sum of the parts is equal to the whole. I think I'll be able to use that and solve for y. So let me label this, and I'll just call this z. How about? It doesn't really matter what you call it. I'm just going to call it z. I want to find z. From that, I should be able to subtract from 1063 and get y. Okay, let's find z. I have this right triangle down here, or up here rather. And I know that that angle of elevation from that top floor is 17.5 degrees. What else do I know? Well, I found that x was 2,712.5 feet. Again, we're looking at a rectangle here, so I know that this opposite side of this rectangle is going to be congruent. So I know that this is going to be 2,712.5 feet. Okay, this is great. Now I have an adjacent side, I have an angle, I'm trying to find the opposite side. Let's use another tangent function. So now we're going to find z. Okay, and I'll set up this equation. Tangent of 17.5 degrees is equal to opposite over adjacent. That'll be z over 2,712.5. Okay, cool. And this time I'm solving for the opposite side, so I'm just going to multiply both sides by that 2,712.5. And that will give me my z. So now I'm going to carefully type this into my calculator. 2,712.5, multiply that by tangent of 17.5. And here's what I get for z. I get that z is approximately equal to 855.2 feet. All right, and that's good because now I know what z is. I can solve for y now. So last step here, I'll do it over here. Let's find y. And this is, remember, this is going to be the height of the approximate height of the top floor of the hotel building. So the last thing we're going to do is we know that y, maybe I'll color code this, y plus z is going to be equal to 1063. Okay. Here is z. So I'll substitute that value in. So y plus 855.2 is equal to 1063. And I can just subtract 855.2 from both sides. So 1063 minus 855.2. Y is approximately equal to 207.8 feet. All right, so now I can finally answer that the height of the top floor from the street is about 207.8 feet. All right, now I have both of the things I was asked for. We are done. All right, this is a really good problem to study from. You'll see problems like this on homework, quizzes, tests even maybe. Being able to apply those trig functions and just basic kind of spatial geometric reasoning to solve for some unknown values. Okay, so that wraps up example 8, and that's the last problem for this section. So we'll end it there. Next up, we're going to move into the unit circle, another approach to dealing with and defining trig functions. So I will see you in 7.3 next.